Hello everyone, it's Usman Learn again, and we're back for part 2 of this series, which is the power rule for polynomials. So last lesson we learnt what differentiation is, and we learnt about the power rule, we learnt about the first principles, which is that the gradient at a certain point, which can be denoted as dy over dx, is equal to the limit of h approaching 0 of f of x plus h. It's a little dodgy notation actually. Let's call this f prime of x plus h minus f of x all over h. And we learnt how we could basically use this for any function, and it would give us our derivatives, which is quite useful. However, I did mention at the end of the video that there was a lot quicker way to find the derivatives of some functions. So I'll be going over that today. So first of all, what is a polynomial? A polynomial is any sort of expression that is the sum of x to the power of a constant. For example, x squared is a polynomial. 3x to the 100th minus 7x to the 2 plus 8x to the 71th power. That is a polynomial because it's just the sum of x to the power of some constants. So anything like this, even x plus 2, that is a polynomial. So this power rule can be used on any polynomial, and the power rule basically states that the derivative, so dy over dx, so the derivative of a function that's in the form ax to the nth power equals an x to the n minus 1. So basically what that means is that the power is brought down and multiplied by the constant that's in front of the x and is reduced by 1. So for example, let's say my function is x squared. Well, if I differentiate this, then this is going to give me 2x to the 1, which is 2x. So the 2 has dropped down to in front, and it was reduced to a 1. Let's say it's something like 8x to the 5th power. Well, if I was to differentiate this, this would give me 40x to the 4. So as you can see, this is quite useful, especially when you have long polynomials, like let's say, I don't know, 8x to the 100 minus 5x to the 8th plus 7x to the 2nd power. Well, we can automatically just differentiate this to give us 800x to the 99th minus 40x to the 7th plus 14x, and that is it. So it's quite quick. So how do we prove this? Because I've told you this rule, but obviously, as you know, I don't like to use any kind of rule without proving it first. So let's just say we have any kind of polynomial. So again, just ax to the power of n. Well, to find the derivative of this, we use the first principles. F of x, limit h approaching 0 of f of x plus h minus f of x over h. Top tip, never miss your limit h approaching 0 or your math teacher will slaughter you. So this, then your f prime of x. F prime of x just means the derivative of, it's the same as saying dy over dx. It's a different notation. This is a Newton's notation, dy dx. That is Leibniz's notation. Two people who are co-credited with creating calculus. But anyway, f of x equals a x plus h to the n minus ax to the n over h. Sorry, equals lim h approaching 0, which equals the limit h approaching 0 of... Now, how do you do this generally? Well, we use something called binomial expansion. So that's going to be a, and then it's going to be x to the power of n plus n choose 1 x to the power of n minus 1 plus n choose 2 x to the power of n minus 2, and so on. As many, there's going to be a lot of terms, as many terms as this n is. So if this n has 4 terms, then this thing will contain 5 things. But it doesn't matter, because as you can see later, it's going to cancel nicely. So plus, it's going to go a bunch of different things in the middle until finally we get to n choose n minus 1 of x to the power of 1 plus n choose n, which is just 1, plus 1 x to the power of 0. Let me just check that's right. Oh no, I've made the classic mistake. Actually, let me just move this down. Okay, so this is going to equal limit h approaching 0 a, and then square brackets x to the power of n plus n choose 1, which is just n, so n x to the power of n minus 1 multiplied by h to the power of 1 plus n choose 2 x to the power of n minus 2 times h squared. And what's important to remember is this n minus 2, so this term, the power of this term and the power of this term have to add to n. N minus 2 plus 2 is n, here n minus 1 plus 1 is n, and n plus 0 is n. Then it's a bunch of terms, however many, that the power is plus 1, until finally we get to plus n choose n minus 1 of x to the 1th power multiplied by h to the n minus 1 plus n choose n, which is just 1, as I said earlier. By the way, n choose n minus 1 is also n, I believe. Yeah, so plus 1 times x is 0, which is 1, so we can ignore that, times h, so just h to the power of n. Okay, all this minus a x to the power of n all over h. So that is equal to the limit h approaching 0 of a x to the power of n plus a n x to the n minus 1 h yada 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 all the way until a h to the power of n then minus ax to the n all over h, which then equals the limit of h approaching 0. So this ax to the power of n cancels with this other ax to the power of n. So all we're left with is a n x to the n minus 1 h, however many middle terms there are, until we get to that a h to the power of n all over h. And then what happens is that this h cancels because there's only one of them. However, all the other terms are going to have more than one h, so then they're not going to cancel. So they will all have some number of h's in them. So this will give us limit of h approaching 0 of a n to the power of x n minus 1. That h is cancelled, and everything else is going to have some number of h's in them. Some h's. However, now, because we're not dividing by 0 anymore, we can just plug h directly into them. And because they all have some h's in them and it's all multiplying, they're all going to turn to 0. So the only term we're left with is an to the x n minus 1, which is exactly as the power rule suggests, that the derivative of ax to the n equals an to the x n minus 1. Put a little QED sign to say that we've proved it. I mean, it's not rigorous. I didn't like state conditions or anything, but you get the point. So it's obviously quite useful because we can use it for any polynomials. But there are some functions there are many functions actually that are not polynomials, and we can't differentiate this way. So that's why we still use power rule. Not power rule. Sorry. We still use the first principles amongst a whole host of other things, which I hope to get into later in my series. So next will be, I believe, trig differentiation and some of the proof for that. So see you next time.